So hello engineers, welcome to the new video, and in this particular video we are going to focus on difference between BJTs and JFET. So basically we are going to see the key differences between BJTs and JFETs, and these are the key differences, that is current generation and current equations, output current dependency, input impedance, thermal runaway, then noise sensitivity, switching speed, and at the end we will see the power dissipation. Okay, so these are the 7 points on which we are going to focus on. Okay, so starting with the very first point, that is current generation and the current equation. Okay, so in case of BJT, I had dedicated a separate course for BJTs, and if you could remember, in case of BJTs, we all know at its base side it has holes, and to the end side, that is to the emitter side, it has a large number of electrons. So let me just show that. Okay, I'll just show 2-3 electrons. Okay, so these are the electrons which are present in the at the emitter side, right? Now obviously this acts like a PN junction diode. If we provide positive over here and negative over here, that means if we provide positive to the base and a negative to the emitter, so there is one current flowing between base and emitter junction, right? But in this particular scenario, what is going to happen? Whatever the holes that is present over here to the base side, it will come over here to the emitter side, and this particular electron, it will move in this particular direction to the base. Okay, and let's suppose if I had not applied any voltage to the collector side, so eventually you can see that this particular electron, it will come to the base side and then it will move in this particular direction, right? So basically if electron is moving in this particular direction, so obviously there is one current flowing in this particular direction. That particular current is known as what? IB, or the base current, right? But in amplifier and during switching operations as well, we generally apply voltage over here, which is known as VCC, right? So whatever the electrons that is present at the emitter side, if it wants to move to the collector side, it can easily move to the collector side as well, provided if we had applied voltage over here, right? So what we can see over here in this both scenario is that, just a second, let me erase this particular arrow. Yeah, what we can see in both of this particular scenario is that for generation of base current, we require both carriers, that is electrons and holes, right? So that's why I had intentionally written over here is that that is minority carriers. Okay, for generation of the base current, we require minority carriers, and for generation of the collector current, we require majority carriers. And basically our emitter current is summation of both the carriers, both the currents, that is IC plus IB, and we all know that for base current both the carriers participate in the generation of current. Okay, and for the collector, only electrons participate. I won't say only electron, but there would be certain holes as well. Okay, we don't need to go in that detail way over here, because this is the key differences video. Okay, I'd explain this particular part in detail way in my BJT course, right, if you could remember. So what we can say is that a current flowing through the BJT is basically because of the two carriers that are flowing through it, that is the minority carriers and the majority carriers. Okay, as far as NPN transistor is concerned, so the majority carrier is electron, right, and the minority carrier is holes, right? So what we can say is that in case of BJTs, okay, or rather why BJT is known as bipolar device, BJTs, which is also known as bipolar device, bipolar junction transistor. Okay, bipolar junction transistor, I'll write it in short form. Okay, so here is that particular point, that why exactly it is known as bipolar. Bi means what? Two, right? Bi means what? Two, and polar means what? Two charges or two carriers. Two charges, I'll write charges, right? And two charges means what? I'm talking about the carriers. Two charges means I'm talking about the carriers, right? So for generation of current in BJTs, we require two carriers. Okay, I'll write over here. Just a second, let me add one more slide. Yeah. So for generation of current in case of BJTs, for generation of current in case of BJTs, we require what? We require two carriers, right? Two carriers, that is minority charge carriers and majority charge carriers, right? Great. Now we will focus on JFET, how exactly things work there. So it's quite simple. We just need to provide this particular voltage VDD between the drain and source. right? This particular voltage between drain and source, and if let's assume for some reasons we had shorted, or rather the VGS is straight away 0. If our VGS is 0, right? So what we can say is that these particular holes are also present in case of JFET, but they are just taking part in the formation of depletion region. They are not at all taking part in the formation of current or generation of current, right? I had explained this particular part, like working and internal structure and all. So in that particular scenario, what we saw was that this particular electrons are responsible to generate the current, that is current ID. Holes don't take part in the generation of current, rather they just focus on taking part in the depletion region, right? So what we can say is that in case of JFET, only electrons or the majority charge carriers, obviously you can clearly see that n channel, the width of n channel is greater as compared to the p channel, right? So if its width is greater, so that means what? That means electrons accumulated in the n channel would be more, and that would be the majority charge carriers, right? So what we can say is that JFET is known as unipolar. First of all, let me write over here. JFET, it is known as what? Unipolar device. In case of BJTs, it was known as bipolar, but in case of JFET, it is known as unipolar. Why unipolar? Sorry, just a second. Yeah, why unipolar? Uni means what? Uni means single. Let me write over here. Uni means single or only one, and polar means charge, right? Polar means charge. So only one charge or the one majority carriers or the one majority charge carriers are taking part in the formation of current. So that's why it is known as unipolar. Okay. So let me write over here, for generation of current or for current generation in case of JFET, for current generation in JFETs, only majority charge carriers take part. Okay, and I'm talking about electron in case of n channel. In case of p channel, it would be holes, right? But the concept remains the same, right? Only one charge is taking the part. Okay, if it is p channel, holes will take the part in the formation of current. If it's n channel, then electrons will take part in the formation of current, right? Great. I hope everything is crystal clear up till here. Now let's move further. Yeah, just a second. Yeah, so now coming to the second point, that is dependency of what? Just a second. Yeah, output current dependency. Okay, so this is another good point to highlight. So we all know in case of BJTs, so let me write over here, when I'm talking about BJTs, when I'm talking about BJTs, just a second. Yeah, when I'm talking about BJTs, so let me highlight it first. So we all know the current equation for BJT for NPN for NPN transistor, that is IC, the output current, it is equivalent to beta times of IB, right? So my IC is the output current, right? IC is the output current, this IB is the input current, right? And this beta is the gain, basically, right? If you could remember. So what we can say is that my output current, it is dependent on the input current. So this was the equation. So instead of this, I can also say that my output current IC, it is proportional to the input current, right? So if my input current is increasing, so the output current should also increase. On contrary, if my input current is decreasing, so the output current should also decrease, right? So this is the basic understanding of the proportionality, right? So this is the point that we need to highlight. Great. All right. So let's come to the JFETs. In case of JFETs, the things work little different. So let me write it properly. JFETs, not so good. My handwriting is not that good, but still try to understand the concept. In case of JFETs, let me highlight this particular point as well. So in case of JFETs, we all know the current equation of JFET, that is Shockley's equation. It is equivalent to ID, which is equivalent to IDSS. Just a second, let me write it properly. Yeah, ID, it is equivalent to IDSS, which is also known as drain to source saturation current, into 1 minus of 1 minus of VGS by VPD whole square. VGS by VPD whole square. So with this particular equation, what I can say is that my output current ID, it is dependent on VGS square, right? So again over here, what does that means? That means if my input voltage VGS increases, so the output current ID also increases, right? On contrary, if my input voltage VGS decreases, so the output current ID also decreases. So this is what it means, right? So I will also highlight this particular point because we would require this particular points in the upcoming key differences, right? So let me move further. Okay, so we had completed the second point as well. Great. So till now we had completed these 2 points. Now let's move to the another key difference. Okay, so before moving to the another key difference, I would also like to highlight one more point. See, this is my BJT, this is my JFET, and this is how it is represented symbol wise, right? So BJT, the terminals that are involved in case of BJTs, they are base, collector, and this is emitter. Okay, obviously if we are dealing with CE amplifier or rather CE configuration. When it comes to JFET, if we are dealing with common source configuration, so this is gate, right? This is source and this is drain. Okay, and just now we saw that our input current is actually controlling the output current. How exactly it is controlling the output current? For that, this is the equation which I had written over here, right? So my output current is dependent on the input current, or rather my input current is controlling the output current. So in other words, what I can say is that my BJT is what? My BJT is current control current source. Okay, so let me just move this particular JFET point little down, and let me just bring this particular box somewhere over here because I would like to write one more point over here. Okay, so when it comes to BJTs, let me just separate them with the help of one line. Okay, so when it comes to BJTs are what? Current control current device. BJTs are current controlled current device or current control current source. CCCS, current control current source. Why? Because this particular current IB, it is controlling the output current. Okay, current control, that's why it is known as current controlled current source. Great. And when it comes to JFET is known as VCCS, that is voltage controlled current source. So let me write over here, for JFETs it is VCCS. JFETs are voltage controlled current source or current device current source. Okay, why voltage control? Oh, sorry. So you are CE. Okay, why it is known as voltage control current source? Because you can clearly see my input voltage is controlling the output current ID. Great. So I hope everything is crystal clear up till here, and you can also see it with the help of this particular diagram. See, this is my input current IB, it is controlling the output current IC, which is also known as GMV pi, right? GMV pi. Okay, great. And in case of JFET, you can clearly see my input voltage VGS. Okay, there isn't any current flowing through the gate. You can clearly see this particular current, it is straight away 0, and the reason is quite simple. I had already explained. This is because the gate and source terminal, I mean gate to source voltage, it is applied in reverse condition. Okay, or that gate to source junction, it is reverse bias. Okay, so that's why the current flowing between gate and source, it would be straight away 0, although practically it is in few nanoamperes. But rather than considering that particular current which is in few nanoamperes, we consider it to be 0, right? So we represent this particular JFET model in this way, that is the gate and source terminal, they are not connected internally. Okay, great. And if they are not connected internally, that means whatever the voltage that we are applying to the input side of the JFET, it will straight away reflect to the gate source terminal, right? So this is that particular voltage VGS, and this particular voltage is actually controlling the output current GM VGS. Okay, which is also known as ID. Great. Okay, I hope everything is crystal clear. Okay, great. Now let's move further and we'll talk about the third point, that is input impedance. Right. So for BJT, so this is our BJT model. Let me just write over here. So this is my BJT model. Okay, BJT AC model of BJT, and this is my AC model of JFET. Right. So let me just move this VGS somewhere over here. All right, great. So now when I talk about the this particular input impedance, so let me just mark it with some arrow. Yeah, and let me just copy. Let's see if I'm able to copy this particular thing. Yeah, bring this somewhere over here. Yeah, that's fine. Just a second, let just give me a few minutes. Alright, so now when I'm talking about the input impedance which is being offered by BJTs, we all know it's almost equal to HIE or RPi. It's somewhat same. Okay, I had already explained in the BJT course. HIE, which is also known as RPi. Okay, it is beta times of 1 plus beta times or beta times of RE. Okay, beta times of RE, right? And we had also seen with the help of data sheet, you know, if we took a rough estimation, it's roughly around 2.6 kilo ohms, but in data sheet they had specifically mentioned that it is roughly around 1.6 kilo ohms to around 4 kilo ohms, something like that, right? If you could remember. So this is the, you know, resistance or the impedance offered by the input terminal of the BJTs, right? But when it comes to JFETs, things are literally change. Why? Because we you know, with the help of this particular voltage VGS, okay, what we had done, we had actually made this particular junction as reverse bias, and since it is acting as a reverse bias, so there isn't any current flowing through the gate source terminal, right? And when I say that the current IG is 0, right, there would be certain voltage VGS. Okay, let's assume that particular voltage is X for a time being. Okay, then what would be the resistance? So the resistance would be R is equivalent to V by I, VGS by IG, VGS by IG. Great. So what is VGS? VGS is X, IG is 0, so this value would be infinite. So basically, ideally the resistance or the impedance offered by this particular JFET would be infinite. Ideally the resistance offered by this particular JFET, it would be infinite. So let me just highlight this particular point. Okay, so whenever you will refer my PDF, you would understand each and every point in detailed way. Okay, so this is the input impedance of what? Bipolar junction transistor. So what we can conclude over here is that input impedance of BJT is quite less than JFET. That means what? For amplification, it's not a good idea to use BJTs. Why? Because we all know for an amplifier, you know, to suck all the signal or to get all the signal from whatever the source that it is extracting, the input impedance of the amplifier should be as high as possible. Again, we had seen this particular concept in one of our session, if you could remember. Okay, so that's why, you know, that's why I'm explaining each and every topic in detail way, and I had already explained these particular topics. Okay, and now what we are doing, we are just comparing few of the differences by taking certain conclusions and all from that particular topics which we had discussed earlier. Okay, so let me just write over here. So what we can write over here is that the input impedance of BJTs, or the, I'll write in this only, the input impedance of BJT, input impedance or input resistance, whatever it may be, the input impedance of BJT is very less as compared to what? As compared to the output impedance, right? To the output as compared to the input impedance of JFET, to the input impedance as compared to the input impedance of JFET, right? As compared to the input impedance of JFET. So let me just write over here in this way, that is my R BJT, R input, RIN of BJT, it is very less as compared to the RI of JFET. Great. So this is the conclusion from the previous point. Okay, I hope you are able to understand each and every point up till here. Let me highlight this particular point as well, and then we will proceed further. Okay, so let me move to the previous slide, and let me just tick those points which we had completed. So till now we had completed this point, and this point. We are still left with the 4 points. So what I will do is that instead of these 2 points, I will first explain these 2. Okay, and then we will focus on the last 2 points. Okay, so let me proceed further. Okay, let me proceed further. Yeah, for just a second, just to show this particular point in proper way, what I will write is that I'll write it in this way, that is the impedance offered by the BJT, it is finite, whereas the impedance offered by the, just a second, finite, yeah, whereas the impedance offered by the JFET, it is infinite, ideally infinite. I will write over here specifically, ideally it is infinite, but generally practically it is in a few, I mean not few, but in mega ohms, maybe 1 mega ohm, 10 mega ohm, something like that. Okay, great. So now that we had completed these particular points, now we will focus on power dissipation. Okay, that means input power dissipation. That means power dissipation, either it is high in case of BJTs or it is high in case of JFETs. Okay, why I'm discussing this particular point? Because it is related to heat generation, because we all know power and heat has certain relation, right? I'm not explaining that formula and all. Okay, because I hope you all guys are familiar with that particular point which we had discussed in my courses, right? What is the relation between power and heat? So when it comes to power, what is the formula for power? So let me just write the formula for power. We all know power, P, it is equivalent to V, that is voltage, into current I, right? Great. Now talking about BJTs, so let me write over here for BJTs, and for FETs. I'll write FETs over here for JFETs rather. Instead of FETs, I'll write JFETs. Okay, great. So when it comes to power dissipated by the BJTs, I mean the input power, right? So P I, that means I'm talking about the input terminals for BJT. Pi for BJT is equivalent to VB or Vin into In. Okay, we all know BJT consumes certain voltage to generate this particular current IB. If you could remember the relation between VBE and IB, right? So it was something like that. So after 0.7 volts, it is going to conduct. If you could remember this particular graph, so it is VBE into IB, right? Into IB. Great. When it comes to FETs or JFETs, to be precise, I'll talk about JFETs. We all know power dissipated in case of JFET, it is equivalent to V in into I in, right? In case of JFET or the V in, it is VGS, right? In case of JFET, the V in is equivalent to VGS, and what is I in? I in is IG, which is equivalent to 0, right? So ideal, this is again an ideal condition. Our IG is 0 in case of JFET. So for JFET, the IG or the gate current is 0, and when I say that the gate current or the IG is 0, so therefore the power dissipated in case of JFETs, Pi, power dissipated in case of JFETs, obviously in case of JFET. So let me just write over here. Okay, power dissipated in case of JFET, it would be 0 ideally. Let me write over here. Oh, sorry. Let me erase this particular point. Yeah, and let me write it in this way. It is 0. Okay, but this is ideal condition. Ideally, this is ideal condition, and let me just highlight these 2 particular points. It's pretty important. Okay, in case of JFET, there would be certain value existing for this particular power dissipation. Okay, so some value, I'll write over here some value. This would be, there would be some value available for the power dissipation when it comes to BJTs, right? So this is my Pi for BJT, and this is my Pi for JFET. So let me just highlight these particular points. Okay, so this is Pi for BJTs. Let me extend it up, and this is Pi for JFETs. Great. And let me write over here. Let me, for that I'll need one more slide. Yeah. So the heat generated by BJTs, or generation of heat, would be greater, or would be much large just a second. First of all, let me write it in this way. Power dissipation, power dissipation would be greater, or it would be maximum in case of, or it would be maximum in case of BJTs, right? In case of BJTs, okay. Whereas JFET hardly consumes any power. Hardly just a second. Hardly consumes any power. Okay. I mean, ideally it would consume zero power, but it's not, it's not the proper way, right? Because if there is certain voltage drop, so obviously there would be certain current existing between two terminals, okay. And when I say that there is certain current available, so obviously there would be certain voltage drop across that particular two terminals, right? So this is the ideal condition. I had intentionally written over here ideal, okay. Otherwise you will think that power dissipation is next to zero, or rather it is zero. It's not a true condition, it's the ideal case, right? There would be certain voltage drop. I mean, there is voltage drop across JFET, I mean the gate source terminal, but there would be also certain current which would be in nanoamperes flowing through the gate source terminal, and due to which there would be power dissipation, right? And due to this particular reason, heat generated, or generation of heat, would be greater. Why? Because we all know power is proportional to, let me write over here, power generated or power dissipated, it is proportional to the heat, right? So if the heat is increasing, that means power is dissipated by that particular resistor, right? If I increase the power across that particular resistor, or voltage across that particular resistor, right? We all know P is equivalent to V into I. So let's suppose if there is one resistor, and if I'm increasing this particular voltage across that particular resistor, so you can see that after some time, or after certain time, this particular resistor will burn out. Why exactly it is happening? Because its power is increasing, and as its power is increasing, so therefore the heat dissipated by that particular resistor increases, and eventually it burns out. I hope you might have seen this particular scenario in most of the YouTube videos and all, okay. Great. So what I can say is that with this particular relation, heat dissipation or generation, or generation, or whatever you can say, heat dissipation or generation would be more, heat dissipation or generation would be more in case of what? In case of BJTs as compared to JFETs. BJTs as compared to what? As compared to JFETs. Great. So I think you understood everything up till here. Great. So till now we had discussed this particular points, where it is, just a second, yeah, this point. Now we will focus on switching speed, okay. So over here, for switching speed, you need to have a good imagination skills, okay. So let me just tell you, for that, just a second, let me just bring these two models over here. Let me just copy these two models. I know I'm making this particular video which is consuming a lot of time. I should take a break in between, but I'm not taking, because I want to explain each and everything with continuity, so that's why I'm not taking break in between. Just a second. Otherwise I would have made some other video where I would have explained these particular concepts, right? So but I don't want to do this. I want to explain each and every concept about the BJTs and JFETs in one video only. Let me erase this particular part. Yeah, alright. So what we saw in case of BJTs was the input current IB, right? The input current IB, it is controlling the output current IC, right? It is controlling the output current IC. Great. And over here the input voltage VGS, it is controlling the output current ID, right? Output current ID, or capital ID, you can write in that way as well, but generally during small signal analysis we prefer to write small letters only, okay. Any which ways will come to our point. See now what exactly is happening over here. In case of BJTs, if we are providing the current, then only the output current is getting generated. That means what? If my IC, it is equivalent to beta times of IB. So if my IB is 0, right, if my IB is 0, so the IC would be what? IC would also be 0. But things literally changes in case of JFET. So JFET it is equivalent to ID, it is equivalent to IDSS into 1 minus of VGS by VPD whole square, right? So now let's assume my VGS is 0, and when I say my VGS is 0, so my ID is maximum as it is. ID is IDSS, right? ID is maximum. Alright, great. So what we can conclude over here is that as soon as I short this particular gate source voltage, my ID straight away jumps to IDSS, right? But in case of BJTs, what we can say is that as soon as I make the input current as 0, my output current would be straight away 0. The main point to notice over here is that, see, here you just require imagination skills, that think this particular JFET model as maybe what I can say as Harry Potter or something like Iron Man or something like that. Sorry for that, I'm not so good in movies and all, because I hardly watch any movies, especially Hollywood movies. But just try to think in that way, like JFET model is like Harry Potter. He is moving his stick and doing certain magic, right? So this VGS is like a Harry Potter. What I mean to say is that, see, if I move the VGS, so the current ID increases drastically. Okay, I hope you are getting this particular point. See, if you could remember in case of Harry Potter, he was just moving his stick and some magic used to happen, right? And over here as well, if I'm moving VGS very quickly, within a fraction of second or within a fraction of millisecond, the ID is going to change. But in case of BJT, see, if I change IB, so this particular IB will move in this particular direction, and if IB is generated, I mean if IB is getting changed, or if IB is generated, then it will make certain change in case of IC. I hope you are getting this particular point. So over here as well the change is occurring, but the thing is that the change is very slow. I hope you are getting this particular point because of the current. See, this particular VGS is somewhat, it creates a magnetic field, and due to that particular magnetic field, the what I can say, yeah, the depletion layer changes its size, right? If the VGS is decreasing, so the current ID is increasing. Okay, this is because of the kind of magnetic field which is created between the JFET. You can think in that way, like there would be certain magnetic field which will attract the current, and then the current would move in this particular direction. I hope you are able to imagine the things. Okay, so for those who are unable to imagine the things, just consider this particular JFET model, or VGS to be specifically, consider this particular thing as the Harry Potter. What he is doing, Harry Potter or Iron Man, whatever you can imagine, or whatever movies you like, they are just moving their hand or stick, whatever is present in their hand, and some magic is going to happen instantly, very quickly, very instantly, right? Same thing is happening over in case of JFET. We are changing the VGS, and very quickly, or within a fraction of millisecond, it is going to change the output current. In case of BJT, just think that Harry Potter is moving the stick, and after 5 to 6 seconds he will see the result. Okay, I hope you are getting this point. So this is what will happen in case of BJT. We are changing the input current, but after some time means not 1 or 2 hours, maybe 1 or 2 seconds, 3 seconds, right? The output current will change. But in case of JFET, if we change the input parameter, that is VGS, so within maybe 3-4 milliseconds, or maybe 0.1 millisecond, we will see that the output parameter is also getting changed. So basically there is a time difference, right? The switching speed is fast, or JFET has high switching speed as compared to the BJTs. This is what I wanted to conclude. I know this particular part was little tedious for you all guys to understand, so that's why I gave you the example of Harry Potter or some Iron Man movies or something like that. Okay, so by next time if you are watching Iron Man movies or something like that, make sure that they are acting like as JFET. He's just moving his hand and he's getting the result, whatever it may be. Okay, and in case of BJTs, we'll consider the same example. If that Iron Man or Harry Potter, if he's moving his stick or moving his hand, whatever, so after some delay, maybe 3-4 second, 5 second, he will get the result. But at the end he will get the result, that's for sure. Okay, but BJTs are providing certain delay, whereas JFETs are not providing any delay. I hope you are getting, I hope I'm able to explain you this particular part properly, right? So JFET has high switching speed. Let me just conclude this particular point. JFET has high switching speed, JFET has high switching speed as compared to BJTs, right? As compared to BJTs. Okay, great. Everything is crystal clear up till here. I hope you enjoyed everything up till here. Now we are just left with the 2 points, and they are quite interrelated, that is noise and thermal runaway. See, this particular point, thermal runaway, I won't explain in that detailed way because it's a very used topic, and I had explained this particular topic in one of the videos which I had made for courses, right? So just a second. Yeah, let me proceed further. So let me write over here. I had explained the concept of thermal runaway, and BJT is depending on the temperature in one of the video, and that particular video was of around 40 to 50 minutes. If you all guys can remember that particular part. So let me write over here. BJT is more sensitive to temperature. Now I won't explain that how exactly it is, its sensitivity is high, or how exactly it is more sensitive to temperature, because that particular part we had discussed in depth. Okay, so let me just write over here. BJT is more sensitive to temperature, right? BJT is more sensitive to temperature. That means what? As the temperature is increasing, so let me change the color. Yeah, as the temperature increases, so whatever the output current that is present, it will also increase by that particular amount or by certain amount, but obviously the change would be maximum. Okay, so in case of JFET, even in JFET, JFET is also sensitive to temperature, but it is less sensitive as compared to BJT. It is less sensitive to temperature. So let me write over here, JFET is less sensitive. It is less sensitive to temperature. Okay, JFET is less sensitive to temperature. That means if temperature increases by very large amount, so the output current, it will change by very small amount. Okay, so you can clearly see the change. I'm just trying to explain this particular concept with the help of these arrows and all, but I had explained this particular both of the concepts, if you could remember, right? In case of JFET, it was we had derived the equation of Vp minus of VGS, which is 0.63 volts. That was our what, if you could remember, zero temperature drift, right? We had discussed that particular concept. In case of JFET, we had discussed the modulation and all, this thermal runaway and all. So I'm not discussing that particular part over here. We'll just try to keep these particular things as small as sweet and short and sweet as possible, right? So this is my agenda. Okay, so with these two particular statements, what we can say is that, see, BJTs, they are much more sensitive to temperature. That means what? If my temperature, if the surrounding temperature of that particular BJT increases, so the output current also increases drastically, right? So what I can say, this particular current, it increases on its own, but it is unwanted signal, right? It is unwanted current. So basically it is known as what? It is known as noise, right? Okay, it is known as noise. I hope you are getting this particular point. Similarly, in case of JFET, even though the current is increasing drastically, even though the surrounding temperature, it is increasing, but the change in current, or the unwanted signal which is being generated in this particular scenario, again, this is noise, but let me just write over here. Let's assume this is noise. The noise generated by BJT, it is N1, and the noise generated by this particular JFET, it is N2. Okay, it is very less. That means the current generated by this particular JFET, when the surrounding temperature increases, it is very, very less. So what I can say is that N1 is greater than N2. Okay, that means the noisy signal is, or rather BJT is more sensitive to noise as well. I hope you are getting this particular one. See, BJT is more sensitive to temperature. That means if the temperature increases, we will get noisy signal, right? In case of JFET, whatever the the surrounding temperature increases, still we will get the noisy signal, but the noisy signal generated in case of JFET, that would be quite less, or rather very, very less as compared to BJT. Let me write it in this way. That is N1, it is very, very large as compared to N2. So what we can conclude from both of this particular point is that BJT is more sensitive to noise as compared to JFET. So this is our agenda. BJTs are more sensitive. BJTs are more sensitive to noise, as compared to JFETs. Great. Okay. So I really hope that you understood each and every point that we had discussed in this particular session. But still, if you have any doubts, if you are facing any difficulties anywhere, it's my request to you. You please do ask me in the comment section. If you are watching this particular video in course, I mean in Udemy or in some another website, you can ask me in the communication section. Okay, we had discussed each and every point in detailed way, in depth. If you are facing any difficulties anywhere, please do ask me. Okay, so thank you for listening me patiently. I'm ending this video over here. Thank you.